Yeah, hello, I'm David Pommerenke. I'm professor at the Institute of Electronics in TU Graz, and we are preparing a series of short videos based on our electromagnetic compatibility classes. And this video is the first one of a series of maybe 3-4 videos which cover shielding. So why do we want to shield? I'll give you a couple examples. For example, the Earth's magnetic field may disturb a sensor. That's a really low frequency problem, like a DC magnetic field problem. Or we have an oscilloscope probe here in the room and we touch it and we see 50 Hertz. That's coupling from the high voltage lines or normal power lines. It's a high impedance electric field shielding problem. Or we have a radio station, let's say 100 meters away, which gives a frequency of 100 megahertz, and we need to shield that. Or there's just a general goal. We have EMC regulations for emissions and immunity, which we want to fulfill. That's basically all done, and what we do is classical electromagnetic theory. Now what we don't do is, for example, light ingress into an optocoupler. We don't look at that shielding. Or X-ray, shielding against X-ray. That's basically not what we do in this class. We look at classical electromagnetic field ideas for shielding with a focus on electromagnetic compatibility. In this slide, I want to contrast shielding from filtering. In the goal of shielding is to reduce electromagnetic fields, and the goal of filtering is to use voltage and current. Now, the physical question for shielding we have to answer, for example, do you want to shield the electric field or the magnetic field? While, of course, in filtering we look at voltage and current. And then electromagnetic field shielding, we have to look at what type of source do we have? Do we have a high impedance electric field source? Do we have a low impedance magnetic field source? Or do we have a plane wave coming? And critical parameters are always the interaction of material with electromagnetic waves. And the materials in electromagnetics are usually defined by conductivity, permittivity, and permeability. So permeability is a dielectric behavior, permeability is a magnetic behavior. And we have to look at geometries. For example, what's the distance to the source? Is the source very close or 100 kilometers away? Or in electromagnetic, we have polarization. The electric field can be polarized vertically or horizontally or circular. So polarization plays a role. And from the engineering point of view, we always have to know sort of what's the best method, what should we do, and especially what we shouldn't do. Now for filtering, we have different filtering strategy. One is we filter by spectral content. For example, the noise is in a certain frequency range above 100 megahertz and the data is below 20. Then we can simply filter by spectral content, suppressing one. Or we can filter by modal. For example, in differential pair, we can have differential mode and common mode. Most unwanted noise couples in common mode and not in differential. So we can do a modal filtering. Or we can filter by magnitude. Let's say the noise, the signal is this magnitude, 1 volt, but the noise is that high. So then we can filter by clipping the high voltage signals. The engineering is the same question, what to do, what not to do. Okay, typical shielding cases for emissions, we have a source, and we put the source in a shielded box, and the victim would be outside. Or the opposite, we can say with the source is outside, the victim is inside the box, and we want to prevent the electromagnetic fields from the source to couple here. Now, a very interesting aspect is always the connection of the cable, which is not treated in this video, but is treated in other videos. A core idea of all shielding which we teach except very low frequency magnetic shielding is the following thing. We have an initial field. That's the field which is transmitted from maybe a radio antenna, etc. The field impinges on some material like metal. In the metal, because of boundary conditions, currents start to flow, and the flowing currents create a reaction field. And electromagnetic theory, it's often called scattered field. And they add up to create a total field. This is the principal idea which we will follow through nearly all of these examples. Think about, we have a wave coming here, an electrical field in this direction, and a magnetic field in this direction. This gives us a pointing vector in this direction. So this gives us the energy flow in this direction. Now we have a metal wall here, and the metal wall, the tangential electric field must be 0. Because if there would be electric field inside the metal, then of course the charge carriers inside the metal would start moving. because in metal we have free charge carriers. What's one thing, one condition. The other is skin effect. Skin effect means the current will not throw everywhere in the metal, but at higher frequencies the current will pretty much only flow at the surface. Let's say the electric field would come here and create this electric field. So the electric field from here has reached this point. Now this violates boundary conditions. Because it violates boundary condition, a current will flow. The current on the surface metal will create a reaction field. So suddenly we have two fields. We have the initial field coming from here and the field from the reaction. And in our imagination, the best way to think about is that the initial field completely penetrates the metal, but the reaction field is also present. And here both have the same magnitude, but of opposite phase, so they sum up to 0. So the total field is 0 because the initial field just goes through it in our imagination. It creates the reaction field. The reaction field has the same magnitude but of opposite phase. That's why we get a sum of 0. Of course, the reaction field is also visible here because the energy which comes here will be reflected at the metal wall. So we will do a couple of experiments. The experiment will be principle. We take a vector network analyzer. It excites one antenna. The antenna radiates. We have different materials here, and this antenna receives. This will be the general setup, so we're looking at the transmission from here to here and how it's affected by adding materials or by changing polarization. So, without further ado, let's start the experiment. Now we're going to show a part which demonstrates some of the theory. When we have a test setup, we have one transmitting antenna, a receiving antenna, and we connect it to a network analyzer. A network analyzer shows the signal transmission from one antenna to the other. And we're going from 1 GHz to 7 GHz. And the slight roll of the signal is a property of the propagation path, which is very clean. These antennas are so-called Vivaldi antennas. They have nothing to do with the emission, but they're Vivaldi antennas. They're very broadband antennas and they radiate forward. And as we see, the metal is vertical, so the electrical field goes from here to here. And in this antenna, the electric field goes from here to here. So this means the antenna is vertical polarized. So the electric field is like that. And now these antennas are looking at each other, so we have a very good signal transmission. And the vertical scale on the network analyzer is 5 dB a division. So the first test one can do, for example, I hold a big piece of metal in between, and we see the signal is much weaker. The wave still goes from this antenna to this antenna, but because of the surface current density, which is induced by the antenna, the surface current density causes a wave which goes this way and this way. And the wave which goes this way exactly cancels the other wave because its polarization is exactly opposite. So this antenna sees the initial wave and it sees the reaction field wave caused by the current density, and they nearly cancel each other on this side. Now let's take another object. Here we have a big block of styrofoam. It does nothing. Why is that? Well, styrofoam is merely air. It's just a very little bit of plastic, and the interaction between the waves and the plastic is very low, so that pretty much acts at this frequency as air. So now let's take another shielding object. This is just a bunch of metal rods, and there's plastic here and plastic here. And if we put them in here, there's no change. Why there's no change? Well, the reason is the initial field goes here, and there's no reaction field because the vertical polarization is vertical, and it cannot cause a vertical current because the rods are not connected. So in this structure, only current can flow in this direction. So this structure doesn't create a reaction field, and that's why it's transparent for the electromagnetic field. But if I rotate 90 degrees, we see this, just a couple rods, they're nearly as efficient as a metal plate. So they shield 15, 20 dB, they shield very strongly. The reason is simple. The electric field comes here, and due to the boundary condition, currents are caused on the vertical part. And these currents cause a reaction field, and this antenna now sees the initial field plus the reaction field, and the reaction field cancels pretty well. Okay, now let's come to another part. Now the antennas see each other because the polarization is the same. Let's flip one antenna by 90 degrees. Okay, now the antennas are cross-polarized. This is horizontal, this is vertical, so the electric field from here cannot be seen by this antenna. Now we do an interesting experiment, which I think is really good to illustrate reaction field. Now we put the grid in, and the grid itself basically has no effect, because in this case, it doesn't shield this field. But if we shield that field, it also doesn't have a lot of effect, because this cannot receive. Now the interesting thing is if we put it in at 45 degree. Now it's at 45 degree and we see it's like 60 dB reduction. What's going on? Why can a shield suddenly cause a signal to appear? And what happens is this electrical field causes a current at 45 degree, and the current at 45 degree radiates at 45 degree. So the reaction field is 45 degree, and we can do a decomposition into the horizontal component and vertical component. And this way, this 45 degree shield causes that part of the energy of the vertical polarization is transmitted in horizontal polarization, and this can be received. So now this antenna transmits here, but the initial field is not visible, but the reaction field is visible. And so at 45 degree, we get the strongest transmission, which is pretty much 6 dB down. And we recruit another student.
My name is Anton Kern. I'm a student at the TU Graz, specialist student for electrical engineering.
Now imagine we don't have a solid metal piece, but we have a metal piece with a slot. So the current without the slot would flow like here, here, here. This is the current without the slot. But there's a slot, the current cannot flow there. So there must be inverted current here in the slot. This is an inverted current, and the inverted current makes sure that this current gets cancelled, because there's a slot that cannot flow. But the inverted current not only flows in the slot, it has to have closed current loops. So the inverted current would flow also like this. And if we would draw up a sum of both, yeah, then this current would come and make a detour and go here. Here it would be undisturbed. Or the total current would come down, make a detour of here. So this red current, the thick red current, is the sum of the reaction current and the initial current. But what happens on the backside? Now it gets interesting. This is a slot, so this reaction current, this virtual current, also is visible here in the slot because it's thin metal slot. So we would see the same pattern of this current flowing on the backside. But this current on the backside, it would start also to radiate. So what we see as in a perfect metal, we see perfect shield. But in a slotted metal, we see the field which is needed to compensate the current in the slot. So this is the radiation, or this is the antenna current structure, which still continues to radiate.
Hello, this is Sajjad Sadeghi. I'm a postdoctoral researcher at Institute of Electronics at Graz University of Technology. Now I want to show you how current density looks like in the presence of a slot in the metallic plate in the simulation. Now jump into the simulation. So here I want to show you the simulation setup for the plane wave. Here I have a bow-tie antenna, so it's a broadband antenna and its frequency range is from 1 to 3 GHz. For the metallic plate, I use the 1 mm thickness copper wall, and here I placed a horizontal slot in the wall. So it's a 3 centimeter length slot, and it's a horizontal slot. Now I want to show you the simulation result. First, I want to show you the result without a slot. So in this simulation, there is no slot in the metallic plate. So as you can see, we have a maximum or peak in the middle. And if I activate the animation, you can see how current flows along the wall. Also, I want to show you the result for 2 GHz and also 3 GHz. And you can see the number of peaks and null are increased due to increasing the frequency. Then I want to show you the results in the presence of the slot. So here you can see the current density distribution in the presence of the slot in the metallic wall. So the overall pattern is similar to the before, but if we see the slot location, we can see two peaks at the both ends of the slot. And if I switch to the arrows mode, you can see the current lines. So here you can see the current lines. You can see the current pass like this, then the current circulates around the slot and then goes in this direction, and similar for other ends of the slot. Now I want to show you the back of the wall. So this was for the front wall. If I switch to the back wall, you can see the current distribution is weaker, and then we can see the two peaks at the similar location due to the leakage from the front wall. And now I'm switching to the front wall, and I want to show you the result for 2 GHz and for 3 GHz. And for 3 GHz, you can see we have two peaks at the both ends of the slot. And here you can see the overall current density distribution along the wall. Now back to you, David.
Now I put it in here, and we see the peak in the middle of the screen. And now if I rotate it, of course the effect of the slot is much less because the current can easily bypass left and right. So now this plate is pretty much like a perfect plate, but if I go to the 90-degree position, we see the resonance of the slot. And so what we learned from this is, of course, that the imperfection, the slot, forces the current to make detours from the ideal position, and this lack of idealness of the current path causes some field to couple to the back side of the metal plate. I want to explain a certain material which we're going to use in an experiment. This is the material. It's a thin black cloth. It's conductive with a well-defined impedance. We just put it on a piece of styrofoam, mechanical reasons. Think about, we have an electromagnetic wave coming, E field vector, H field vector, propagation direction is here. And for reasons not explained here, if we divide the E field magnitude by the H field magnitude, we will get impedance of 377 ohm in free space. Now imagine that this wave is propagating here, and now if it looks this way, it has 377 ohm, so the wave can propagate without a problem. But now let's say we put another material here. We put a material here which has a 377 square ohm impedance. And what's square ohm impedance? If I cut a square out of this black material and contact here, I will measure 377 ohm. If I take a bigger square, contact here, I also see 377 ohm. It's higher and wider. So this has a square impedance of 377 ohm. Now let's say the material is here, the wave comes, and if the wave comes from here, it sees the 377 ohm of free space, and it sees 377 ohm of the black material. So here, they're looking from here, both are basically in parallel. So the wave will be partially reflected because the impedance from 377 hits an impedance from 377 divided by 2. So now let's do the test. We put it in between. And what do we see? We see a reduction of about 6 dB. As explained before, this is pretty much exactly what we expect for this type of resistive sheet material. And what happens here, the wave comes, and the wave causes a weak reaction field. And the reaction field is measured by this antenna plus the initial field. And because of the fact that this has 377 ohm, there is a cancellation of half of the electric field, which is 6 dB in power. So my hope is that in this video, we were able to introduce you to this idea how shielding can be physically understood by initial field, reaction field, total field, and the reaction field is caused by the boundary conditions.